Hello everyone. What I'm going to attempt to show you is the RomeroUK Muller motor generator accelerating under load. This is difficult to do on a video, but I have to point out a few things first. Okay, I'm just going to raise the camera up a bit here. Over here we have a multimeter. We have our multimeter, and at the moment is basically sitting on 0 volts. It is connected to the supply, but there is no current at this present time being drawn through this resistor. Now I'm going to short out the coils to this resistor, creating a circuit back to the battery through the path of the resistor. At the moment the voltage on the multimeter reads positive. So therefore, if we basically create a short through that resistor back to the supply and create a load, we are going to basically see the voltage polarity symbol here reverse to negative, because the voltage on this side of the resistor is going to become greater than the voltage on that side. This side of the battery is supplying power to the motor to drive it, while on this side of the resistor there's nothing at this point in time. Now there's some rather complex electronics, and I will attempt it after the video, when I present this on the forum, to draw up a schematic to show where and how this is wired. And if you have a careful look up here, I have a digital oscilloscope up on the flat panel LCD mounted on the ceiling, and you can see a very high amplitude sine wave. Now that high amplitude back EMF sine wave that you can see presented up on the screen, I'm going to short out to the battery supply. So while you're watching this, and I will actually take screenshots of that and present that too on the forum. So if you're just watching that, I'll short out the supply. You can see the waveform drop. And if you can hear the motor in the background, you can hear it accelerating. I'll disconnect. I'll stop talking. You can hear the motor decelerate. It picks up about 200 to 300 RPM when we short out the supply. Okay. Now I think the information on the multimeter is probably more relevant. So I'm just going to put the camera down. Now I am going to touch this wire here, which is connected to the diode, which is connected to the junction of the coils, between the coils and the switching FETs, and we're connecting the negative end of the supply rail of the coils through a forward bias diode to the positive end of the battery. So that means that voltage will not conduct until it exceeds the supply rail of the batteries. In other words, I got 24 volt. I got two 12-volt batteries connected in series, making 24 volts. Now the key to this the key to accelerating under load is not to basically short out the generated EMF, the generated voltage generated by the coils. We must stay above the voltage of the load. So if you're just watching the multimeter, now you're seeing current being drawn through the load resistor to the battery. Now if I connect it to the negative end of the battery, you'll hear the motor load down and slow down. You can hear it slowing down. That's because we've gone below the potential of the supply. Now I can still go to the negative end of the battery as long as I stay above the supply rail. Now here I have a 32 volt Zener diode, so I will stay now 30 volts above the potential of the supply, and I will short it out to negative supply, and you can also hear it increase in speed. Okay, so, and I can feel the diode getting hot in my hands too. It's about, that's about hot enough, I'm afraid. Yeah, so, alright, so I can connect, when I connect it up to the positive end of the battery, we're actually creating a circuit back to the battery but above the potential of the supply, which means we're also above the generated voltage being generated by the coils themselves. And you can hear the motor picking up an RPM, and you can see this is the load voltage across the resistor. Now this is a 3 ohm load resistor, so if you do the simple Ohm's law, V over R, you'll get I. So pretty much basically if you take that value on there and divide it by 3, you know that will present the current going back to the supply. So we're actually charging the supply while increasing the speed of the motor. And funny enough, I've got 2 coils here driving this thing. So when I engage the second drive coil, which I'll do now, you'll see, watch the multimeter and hear the RPM pick up. We are now, this is not, I want to stress here, this is not over unity, and we are getting into more complex equations and power circuits and stuff like that. This is not over unity at this point. What I'm doing here is coil 1 is actually now providing enough power to drive coil 2 according to the current that's basically now being presented, the voltage being presented on the meter. And if I disconnect this, you can hear it speed up a little bit more. That's because the second circuit is now being driven off the battery, not off coil 2. I'll disengage the second drive coil. Now I think this is something. This is some of the key to basically the violation of Lenz's law. What I believe is happening is that we're extracting the voltage generated by the coil when the field collapses. Now at that point when the field collapses, the voltage is in reverse, so therefore by grounding that out, we're creating a magnetic field which is in violation of Lenz's law, which makes the motor run faster. I've sat down with pen and paper and worked through it. The best I can understand is those very small milliamps that we're seeing on the multimeter right now is generating a small amount of magnetic field in violation of Lenz's law, which is pushing our motor around a little bit faster because we're actually grounding out the voltage, the reverse voltage, as it's basically being kicked back from the coils. Okay, I'll leave it there for now. See how we go.